So let me again briefly go through the computation. So our Lagrangian was our Lagrangian for particle in the electromagnetic field, okay, was free particle Lagrangian, free part, okay, that is given by minus mc square, okay, minus mc square and square root of 1 minus v square upon c square. Okay. Then there is a interacting part, okay, which is written as E by C, A vector potential A dot V, okay, minus E and scalar potential. Okay, and I will consider the Euler-Lagrange equation for this. Okay, so but before calculating Euler-Lagrange equation, anyway we need to calculate this term del L by del xi dot. Okay, this is nothing but your canonical momentum. Okay, so I will just I will just mention few things about the canonical momenta. Okay, del L by del xi dot, okay, is del L by del xi dot of this term and del L by del xi dot of this term. Okay, so I need to calculate these two terms. Okay, the expression for when I take derivative of this term, what I am going to get is pi, usual pi. Okay, your momenta where pi is equal to m gamma vi, where vi are three velocities. Okay, so this is my first term. This will be my first term. In fact, I will get a minus pi. Okay. And when I operate del del xi dot on this term, this will give me 0, and this term will give me minus e by c, okay, minus e by c ai. Okay. This is what we will get. Okay, so if I equate this with equal to canonical momenta, okay, and I will put extra minus sign because see these are the lower indices. Okay, so usually we define canonical momenta p as del L by del x dot. Okay, so I will put usual minus sign, extra minus sign here, and it will clear to you why I am putting. Okay, I will call this as canonical momenta pi. Okay, so my canonical momenta p vector is all these in lower indices, so I can write it in upper indices. If I want to write it in upper indices, so this will be, this is, so I can write this as this will be, so let me rewrite this. So canonical momenta with lower indices, so if I eat this minus sign, then it will be ei plus e by c ai, and this is same as writing pi equal to pi plus e by c ai, which is nothing but in the vector notation it will be vector p equal to vector small p plus e by c vector a. Okay, now so this is our canonical momenta, capital P. Okay, suppose we are discussing a free particle. Okay, correct, in the free particle. Okay, suppose if I have expression which depends on, then I will have only this small p. Okay, if my particle is was free, then I will have only this small p. Okay, now if there is only magnetic field, if there is only magnetic field, no electric field, if there is only magnetic field, okay, then what is your free particle, whatever the expression you have for free particle which depends only on say p. Okay, suppose this is some expression of a free particle which depends only on this p. Okay, I will get the corresponding expression for a particle in a magnetic field by replacing this P, okay, by the canonical moment of P minus E by C A. Okay, so this is a very short cut to achieve the result of a particle moving in a magnetic field from the corresponding result for a particle which is freely moving relativistic particle. Okay, so I'll just replace wherever this mechanical moment is coming, okay, which was canonical momenta for a free particle. I will just replace that by canonical momenta minus E by Ca. That's it, and I will recover all the results. I will illustrate more about this. Okay. So this is my canonical momentum. So this is my canonical momentum. Okay. Yeah. Now let us go about the equation of motion. Okay. So d dt of, so I need d dt of del L by del xi dot. Okay. That means d dt of pi. Now whether I will write in upper or lower, it doesn't matter once we have this relation. Okay. So it will be pi, okay, plus E by C ai. Okay. So this will be equal to dpi by dt, okay, plus E by C dai by dt. Okay, but since a is a function of time and space both, okay, dai by dt is equal to, okay, partial derivative of ai with respect to t, okay, plus dxi by dt, that is your usual velocity, dxi by dt, that is your usual velocity vi, into del ai del xi. Okay, so this is equal to, so this I will also write d del by del t, okay, plus vi del I. So I should use here a different index j. Okay, vj del j ai. Okay, yeah. So this is the expression for dai by dt. We have this relation. So now we know what is d dt of del del xi dot. Okay, so d dt of del del xi dot is equal to dpi by dt, okay, plus del ai by del t, okay, plus vj del j ai. Okay. Right. Now let us consider. The derivative with respect to del xi. Okay, because in Euler Lagrange equation we have this term minus del L by del xi. Okay, so let us go about that. Let us see. So del L by del xi, I am calculating this term now. Okay, so this will be equal to del xi of what? Del xi of this term and this term. Okay, so this will be E by C a dot v. A dot v is aj vj, okay, minus e phi. Okay, so this is equal to E by C, okay, E by C Vj, okay, So this will act on AI, AJ, and this will act on this del xi will act on Vj, but del Vj by del xi is 0, right? Because Vj's are independent functions of xi's. Okay? So this will be 0. Okay? So I will get Vj. I will first write Vj and del I Aj. Okay, so this is the first term minus E del I phi. Okay, so this is my del xi. Is that clear? Okay. Therefore, the Euler-Lagrange equation, that is d dt of del L by del xi dot minus del L by del xi is equal to what? The first part, which is dpi by dt, okay, plus E by C del AI by del T, plus E by C Vj del J AI, okay, minus E by C. So E by C I have taken common, Vj del I Aj, okay, and minus plus E del I phi equal to 0. Okay. Fine. Okay. So I will collect now this term with this term. Okay, and this term I will keep separate. So this implies dpi by dt, okay, plus E times del I phi, okay, plus 1 over C del AI by del T, okay, plus E by C Vj del J AI minus Vj del I Aj, okay, equal to 0. Okay. Now let us concentrate about this term. Let us concentrate about this term. Okay. So this term one can actually write. Okay. So let us consider del cross, okay, usual. Sorry. Let us consider V cross del cross A and its ith component. Okay. So I am talking about ith component of this expression. Okay, so ith component of this expression I can write as epsilon I j k, okay, Vj del cross A its kth component. Okay, this is equal to epsilon I j k, okay, Vj, okay, del cross A kth component, that is given by epsilon k L m del L, because this in our notation this is equal to del L and A m. Okay, so this is equal to epsilon I j k epsilon k L m Vj del L A m. Okay, but epsilon I j k epsilon I k L m, epsilon I j k epsilon k L m, you can write as this is antisymmetric in Ij, antisymmetric in Lm, and k is summed over. So k should not appear on the right hand side, and the right hand side expression should be antisymmetric in Ij and Lm. Okay, so that I will write as there is no It depends on the situation whether you should express this in terms of Kronecker delta or not. Okay, so here it is fruitful to express this expression product of two epsilons into Kronecker delta, but I have to take into account the antisymmetry property of this. So I L delta J M minus delta I M delta J L. So you can see that this expression is antisymmetric in Ij and antisymmetric in Lm. In fact, if it is antisymmetric in Ij, it's automatically antisymmetric in Lm. And then I will write the next expression Vj del L Am. Okay, so this is equal to this part when multiplied with this part. Okay, I should replace L by I and M by J. So Vj L by I will get del I and M by J Aj. Okay, minus I by M by I and L by J. So it is Vj del J Vj del J Vj del J and Ai. That's it. So you see that this term Vj del J Ai minus Vj del I Aj, Vj del J Ai with minus sign and plus Vj del I Aj. So this implies that this quantity, this quantity, Vj del J Ai minus Vj del I Aj is nothing but minus of the ith component of V cross del cross A. Okay, so this I can replace by minus of ith component of this expression. But what is del cross A? Del cross A, now you use the following expression. Use B equal to del cross A, known expression for B in terms of A, and B and E in terms of A and phi. And what is E? E is, I hope you know this, gradient of phi minus 1 over C del A by del T. Okay, is that clear? Okay, so the previous expression here, this expression will become minus V cross B ith component. Okay, and this expression is minus EI. Okay, so I have dpi by dt is equal to is dpi by dt minus E times ith component of electric field minus V cross B E by C and ith component of V cross B equal to 0. So this implies that dpi by dt is equal to E into EI plus E by C into V cross B I. Okay. In other words, in the vector notation, dP by dt is equal to E plus E by C Okay, so this is our Lorentz force law. Okay. So we recovered the Lorentz force law from the starting from the action of a relativistic particle in electromagnetic field. Okay. Any doubt so far? Any confusion or any question? Hmm? I hope there is no question. Okay, so I will proceed. So we have no equation of motion. As a this Lorentz force law is coming as an equation of motion. Okay, derived from the as a Euler Lagrange equation of motion derived from the action. Now let us concentrate about the Hamiltonian. Okay, so the Hamiltonian H is P. Okay. Hamiltonian H is P, but this P is actually the canonical momenta, right? In the description of Hamiltonian framework, okay, while going from Hamiltonian to Lagrangian, we use canonical momenta in the Legendre transformation. Okay, so it is P dot V okay, minus L. Okay, clear? Now, note that this P, capital P, is small p plus E by C, no, not E, yeah, E by C A. Okay, clear? Okay. Now, what we need to do, we need to express these velocities to calculate the Hamiltonian. We need to express these velocities in terms of this capital P and also the Lagrangian in terms of this capital P. Okay, fine. Okay, so you use the following relation. Okay, you use P equal to M gamma V. Okay, and you invert this. Okay, so you write V as, okay, so from this relation you will get V square as, okay, I already mentioned this. Let me write V square as P square C square P square into P square plus M square C square. Okay, so you get V square from this. Use this relation, okay, and square it. Okay, so this implies the gamma, which is 1 over square root of 1 minus V square divided by C square, is equal to square root of P square plus M square C square divided by MC. This is what you are going to get for gamma. So now your job is done. Okay, so use this relation, okay, here, okay, to express V, vector V. Vector V is what? P divided by M gamma. Okay, so now you know gamma in terms of P, substitute here. So that means you have inverted V, you have converted V in terms of P, small p. Okay, but one can always replace this small p, use this relation to replace small p by capital P minus this factor. Okay, so if you do that and you do the same thing in the L also. Okay, so if you do everything, okay, the calculation for converting, okay, so let me mention few things. So from these expressions, from this expression is when you use this here, okay, and when you take dot of V with capital P, you will get the following: P dot V will be equal to C times capital P minus E by C A dot capital P divided by square root of capital P minus E by C A square, okay, plus M square C square. This is what you are going to get for P dot P. Okay, and for you also express L in terms of P and X. Okay, so you'll get this time you'll get minus M square C cube divided by capital P minus E by C vector A square plus M square C square plus E into A dot vector P minus E by C A divided by square root of P minus E by C A square plus M square C square is a half square root, okay, minus E phi. Okay, so you have this relation, you have this relation, okay, and then you use this Legendre transformation to calculate H. Okay, so I will leave it to you to derive this, okay, and then use this relation in the definition of H, and you will get H is equal to H as P vector P minus E by C vector A square, okay, C square plus M square C to the power 4 plus E phi. Okay, so this is your H. Okay, so now you compare this H. This is my, if you want to say this as energy, this is your total energy. Okay, now if you compare this with the expression for a free particle, what will be the expression? P square C square, where P square is vector P dot P plus M square C to the power 4. Okay, clear? In this notation, if you know this relation, okay, we also have this 4 momentum P mu, which is E by C and this. Okay, so you see this E is actually zeroth. E actually transform as a zeroth component of 4 momentum. Okay, for relativistic free particle. Now, if I want to make a comparison for a relativistic free particle in electromagnetic field, I have this as my energy. Okay. Now I want to define something like this, the 4 momentum for this particle. How should I define? So I can define this in the following way. Okay, I can suppose if I call this as say W. Okay, so I will consider W minus E phi square equal to, if I take this side here, and instead of H, H is the Hamiltonian, which I am calling as W instead of calling energy. So W minus E phi, and I will make square of it. It will be P minus E by C A square C square plus M square C to the power 4. Okay, so from this I can take this C here, okay, and rearrange. So I will get, I can write this as P capital mu capital P mu, capital P lower mu equal to m square c square. Okay, here I will get P mu equal to m square c square. So you see that W minus E phi divided by C is actually your zeroth component of zeroth component of this vector P mu. So I will define my P mu, vector P mu, as W minus E phi divided by C and capital P minus E by C A. So now you see these substitutions. Okay, energy is replaced by energy minus E phi, the scalar potential, and momentum, usual momentum, is replaced by canonical momentum minus E by C A. Okay. These replacement will again give me P mu as m square c square. Okay. Is it clear? Okay. So you see the kinetic energy of reduced particle in electromagnetic field, okay, is given by this. This is this is my total energy. Then the kinetic energy part will be this only, right? That is W minus E phi. And the momentum part will be given by canonical momentum minus E by C A. Is it clear? So when I write this relation, okay, this is my spatial component of this vector, this 4 vector, and this is my zeroth component of this 4 vector. So there are several p's which are occurring. Okay, so you should be careful. This is your canonical momentum. Okay, in that sense, you say this is my canonical energy. Okay, if I subtract from those canonical momentum and canonical energy the respective scalar field and vector field, vector potential, I will get this relation. The resulting for momentum will satisfy this relation. So it will be same as your P mu equal to m square c square. Right? So now it is clear that if I consider, say, if I consider the quantity E equal to W minus E phi, okay, if I consider this quantity and if I take its time derivative, will I get 0 or not? Will I get 0 here? Just use your physics. I have a charged particle moving in electromagnetic field, and you should know what is this E, and I just explained what is this E, and I'm taking its time derivative. Will I get 0 or not? Any answer? Will I get 0 or not?
No, sir.
No. So what I am going to get? So it's expected that the charged particle will have to do some work against the electromagnetic field. So some energy will be stored in the field. Okay. So the kinetic energy is not conserved. Okay. So dE by dt, if you calculate dE by dt, you use the equation of motion, okay, and show that dE by dt is actually dE by dt is equal to E times charge into free velocity v into electric field. You can show this. Okay. So ultimately, I have two equations. One is equation of motion dP by dt equal to E electric field plus E by C del A no, E by C V cross P. This is my Lorentz force law supplemented with this energy relation. Okay, so I have these two equations. Is this clear to everyone? So take away lesson from this is that the important thing is that we have reproduced the Lorentz force law. Then this is also expected result. This you know, okay, from your electrodynamics. We derived this using the Lagrangian framework. And one more thing is that your canonical momenta is not equal to canonical momenta is not always equal to mechanical momenta. Okay. In classical mechanics in first year, okay, you always get the equality between whatever the momenta you derive, okay, from the Lagrangian framework, you always match with your mechanical MV kind of thing. Okay. But these are in the sense generalized momenta. Those generalized momenta or canonical momenta need not be same, need not be equal to mechanical momenta. And this is the best example. Okay. So if, and you see the canonical momenta and mechanical momenta differ by vector potential. It does not include the electric field, the scalar potential. So if I have a particle moving in only magnetic field, okay, time independent magnetic field, because we'll see that if you put time dependence to magnetic field, it leads to electric field. So I don't want that. So just consider time independent magnetic field. Then whatever the expression you get for free particle, you replace the free particle equation involving P by canonical momenta minus E by C A. And you will get the corresponding expression for a relativistic particle in magnetic field. So it's a very short way of shortcut of getting the equations or expressions for a relativistic particle in magnetic field from free relativistic particle. You don't have to do, you can just bypass all this process. Okay, you can just bypass this thing and you just write down the equation for free particle involving momenta and replace that momenta by canonical momenta minus E by C A. That's it. Is that clear?
Sir?
Sir,
so this canonical, my canonical four momenta and my mechanical four momenta, so they are consistent in the sense their scalar product are, means with itself is always m square c square.
Yes, yes. So that is the,
Sir,
now we want the scalar combination. We want some invariances. This is one of the invariants. P mu equal to m square c square.
Can you please explain how capital P mu is m square c square, that part?
Capital P mu is m square c is here, right? So where I have defined here. Okay. So capital P mu, just let us write. Okay. So capital P mu is capital P mu is equal to what? P0 minus so I have to, this P is different than this canonical. Huh? So let me write this as script vector P and script vector P. Okay, clear? So here I will this P, this is the zeroth component and this is spatial component. Okay, so let me write this as this entire thing as script capital P. Okay, this is same as your mechanical momentum if you see. Okay, so P0 minus P dot P. Okay, so P0 is your W minus E phi by C square minus P dot P. P is uh, canonical momenta minus E by C A dotted with canonical momenta minus E by C A. And what is this? This relation. This relation is just this, right? Okay.
Sir.
This relation, this whatever I wrote, is just this. Okay, so I'm just, you see, you don't have to prove anything. Okay, just take this on this side and divide by c square. That's it, and redefine this as p0 and this as script p, which is your mechanical momentum. So you will get this relation. The way we constructed this is from this, right? So you take this term on left hand side, you divide by c square. That's it. This is how your this is defined. So P mu is bound to be m square c square by construction. You don't have to prove anything. Is that clear or not?
Okay, so we are means we are assuming this, that this P mu capital P mu by consistency should be always m square c square.
No, it's not assuming. We got this relation. See, there is no assumption while getting this relation, right? After you get this, see, we derived this Hamiltonian. This Hamiltonian is total energy. Call it as W. Okay? If I subtract from W this E5, which I can always do, and square it and divide by c square, then that expression is this expression square plus m square c square. Then it is logical to define a four momentum, capital P mu, whose zeroth component is this, and whose three components are this. That's it. That is what I am doing. So basically, this is, I don't have to define the script P or something. Okay. So it's like this is your this thing P, as I said before, P minus E by C A is your P. Okay. I just define W minus E by phi equal to E. E. Okay. So if I divide by this expression by C, okay, then I will divide it here by C. Okay. This is your usual zeroth component of four momentum. Okay. So now if I define P mu, okay, so you just compare this with this P mu P. Same,
Yes,
right?
sir. Yes, sir. Got it. Yes, sir.
So I'm not doing anything new. I'm just comparing with free particle. Okay. So here also I have natural invariance, okay, which is P mu equal to m square c square. Where this P mu, P0 is this, and the vector P is this. Okay. So when you consider a free particle, okay, your P mu is P0 and usual three momenta. This momenta is replaced by this. That's it. And this P0 is replaced by this quantity. That's it. There is no other, no extra thing. Okay. So you have the 4 momentum, okay, defined in for a particle moving in an external electromagnetic field. And we got these 2 equations of motion. I will call this also equation of motion. In some sense, this is also equation of motion. Okay. Now the question is, can I write how to write or how to express equations of motion in covariant form? You see, these equations are written in 3 vector notation. Okay, they are not written in tensorial notation or 4 vector notation. Okay, and you see that under Lorentz transformation, your any 3 vector, say A, okay, transform. See, your 3 vector transform in a different way than your 4 vector. Say A mu, right? A mu transform like lambda mu nu A nu under Lorentz transformation. How this will transform? Vector A, that means ith component of this vector will be lambda I nu A nu. See the difference between these two. Okay, this extra the A0 will create all the difference. This is any vector, this is not necessarily vector potential. You consider any vector, it will transform under Lorentz transformation like this. Okay. So these are not covariant equations. Covariant in the sense that it's not a relation between 4 vectors or 4 tensors. Okay. Now we want to write in the 4 vector notation. Okay. One thing we know about the 4 vectors is that we know the momentum 4 vector. Okay. E mu. Okay. We know also A mu. Okay. We have these 2 4 vectors. Okay. Remember what is this P mu? P mu is defined as m dx mu by dt. You go back to your original definition of 4 momentum. This is this. Okay, where tau is the proper time, and I have A mu. Now, can I write this expression in terms of, although these are in E and B, okay, can I express them in a covariant way? Obviously, any attempt to express this E in 4 vector is futile. Okay, you have electric field E and magnetic field B. Okay, there is no such a thing called zeroth component of electric field, and there is no such a thing called zeroth component of magnetic field. Electric field and magnetic fields are derived from certain potentials. Those are phi and A. Now, can I write this expression in terms of P mu and A mu, or at least in terms of 4 velocities, which let me write this is U mu. Okay. Is it possible to express this previous equations of motion in terms of these 4 vectors, so that I will get a covariant expression? Okay, so that is our next task. But before coming to that question, okay, we have to write B and E in a slightly different notation, because these equations, as you can see, these equations involve E and B. Okay, so let me consider now. Let me write this E and B in a slightly different way. First, let us consider this relation B. Vector B is curl of A. Okay. In the epsilon ijk notation, it will be epsilon ijk, okay, del j ak. So this is ith component of magnetic field. This will give me ith component of magnetic field. Okay, but you see, this I can write in a following way. This is equal to, okay, this is nothing but this is nothing but, okay, if I take this j up, okay, what I am going to get? This is minus of epsilon ijk. If I take this j up, okay, then I will get minus del j ak. I hope you by this time you should be comfortable, right? Moving this index j up. Okay, I have taken this j up, so I get minus sign here. Epsilon ijk del j ak. Epsilon ijk is not a part of any 4 tensor or something. We will do later on, but as it stands, it is just a symbol. Okay, epsilon ijk is just a symbol. Okay, and remember how this is defined. Epsilon 1, 2, 3 is equal to 1. Okay, for any even permutation of 1, 2, 3, and all permutation of 1, 2, 3 it will be minus 1 and 0 otherwise. Okay, fine. So this expression is equal to minus, now you see, now just see what I am doing, minus epsilon ijk del j ak divided by 2, okay, minus epsilon, see these j and k are summed over, okay, so I will write this second term as minus epsilon I k j del k aj. I have done nothing, okay, I just changed the dummy indices. K is replaced by j and j is replaced by k. But then this is equal to minus half, okay, epsilon. Now I will use the antisymmetry property of epsilon ijk. This thing is nothing but minus of epsilon ijk. Epsilon ikj is minus of epsilon ijk. So that minus sign will become plus here. So I will take epsilon ijk common. I will write minus here, and resultant expression will be del j ak minus del k aj. This is nothing but your curl, you see, written in slightly different form. That's it. Now you define a quantity f. I will write this as fjk. Define fjk as del j ak minus del k aj. Okay, is this clear? Therefore, ith component of magnetic field is minus half epsilon ijk, okay, fjk, which is same as equal to minus half epsilon ijk. If I bring these two, see, ijk all are special indices. If I bring two special indices down, I will get 2 minus sign, which will resultantly give me plus sign. Okay, so it will be same as fjk. Is this clear? So I have expressed magnetic field in terms of some two index object. Is this clear? Okay. Fine. Now similarly, your electric field is equal to minus of gradient of phi minus 1 over c del a by del t, but c times t is x0. Okay, so this is equal to minus gradient of phi minus del a by del x0. Okay. Now I want ith component of electric field. Ith component of electric field will be ith component of this and ith component of this. So ith component of this is conventionally called as del I. You check our notation. Okay. Del I phi minus del AI by del x0. Okay. This is equal to this I will express in the following way. This I will express as write the shorthand notation for del x0, that is del 0 AI. Okay, del 0 AI. Okay. And I will take this I up, so I will get plus here. So I will minus del 0 AI, that is this term, plus del I phi. Okay. But what is phi? Phi is A0, right? You remember A mu is phi and A. Okay, so phi is basically zeroth component of vector potential. Okay, so this I will write as del I A0 minus this 0. If I take up, there is no sign change, so there will be minus del 0 here. Okay. So I will define this as Fi0. Okay. So I defined electric. I express electric field in terms of some one index object Fi0, ith component of electric field. Okay, here. So now you see I have ith component of electric field. Okay, so E1 equal to Ex equal to F10, E2 equal to Ey equal to F20, and E3 equal to Ez equal to F30. And I have magnetic field which is Bi equal to minus half epsilon I jk F jk or F upper jk, doesn't matter. So it gives me, okay, what is B1? B1 equal to Bx. You can show this. Okay, so compute this. B1 equal to Bx. Okay, it's equal to just curl in the right curl notation. So it will be minus del 2 A3 minus del 3 A2. So this is what you will get. Okay. I will do this for you, and rest of the components you should do. So Bx, that means B1, I equal to 1. Okay, I equal to 1. So J can be 2 and 3 only. Okay, so let us consider J equal to 2, K equal to 3. Then it will be F23. Okay, plus, that is minus here, minus half epsilon 1 J equal to 3. These are summed over, so I have to put J2 K3 and J3 K2. So epsilon 1 3 2 F32. Okay, this is equal to, okay, minus half epsilon 1 2 3. Okay, F23, so it will be twice of F23. Okay, what is F23? So it will be 2 will go minus epsilon 1 2 3, that is 1. This is 1, and F23 is F upper 23. This is equal to F23 with minus sign. F23 is by definition is del 2 A3 minus del 3 A2. Okay, this is this. Okay, fine. So you do rest of the thing, B2, B3. Okay, so So I have EI and I have BI expressed in terms of some two index and one index object. But you see, the way we have constructed these objects, okay, I can write down now a a two index object f mu nu, okay, in the following way. If I define f mu nu as del mu nu minus del nu mu, if I define this, okay, then what is your fi0? Fi0 will be del I a0 minus del 0 ai, that is ei. And Fij, okay, what will be your Fij? Fij is del I aj minus del j ai, okay, which is same as this one, which is occurring in the definition of B. Okay, Fi0 in terms of electric field is simple, which is just a definition. So Fi0 is Ei. Ei is Fi0 and Fi0 is Ei. But you see, to express Fjk in terms of Bi is complicated. Okay? So you have to use the definition of epsilon. Okay. So now I want to write this in terms of magnetic field. What is magnetic field? This is magnetic field. Okay. So if I suppose if I multiply, okay, this quantity from the left by epsilon ILM, epsilon IL, okay, BI equal to minus half epsilon ILM epsilon IJK, and instead of writing this FJK down, I will write FJK. Some more JK is implemented, some more I is implemented. So there is a summation or I. There is a summation or I. Okay. This is equal to, you use the product expression. Okay. So if you use that, you will get the FLM. Okay. So you will get, so if you use that here, you will get FLM, okay, with minus. So this implies minus of FLM is equal to BI epsilon ILM. In other words, if I write just in IJ, if I use instead of LM, if I use IJ, then Fij is equal to minus epsilon IJK BK. Okay, so B in terms of F is given by this relation and F in terms of B is given by this relation. They are not same. There is a half difference. Okay, is this clear? So note these relations: this, and this. Okay. If I want to write this in terms of matrix, okay, how should I write? F mu nu as a matrix. Okay. F00. Okay. F00, since by definition it is antisymmetric. It is antisymmetric, right? So all the diagonal components will be 0. Okay. And if F I0, see the way I define Fi0. Fi0 how is defined? Fi0 is del I A0 minus del 0 ai. Then what will be F0i? F0i will be minus of Fi0, right? Okay. So F mu nu is antisymmetric matrix. Okay. And if Fi0s are components of electric field, then F0i. So first index represents row and second column. Okay. So Fi0 will be ith row, 0th column. Those will be electric fields. And F0I will be 0th row and ith column. So that will be minus E1, minus E2, minus E3. Now you look at Fij. Okay. What will be your F110, F220, F330? So what will be F12? F12 will be 1, 2, 3, B3. B3 is BZ, so minus BZ. So it will be minus, this is 0 and this is minus BZ. Okay. Now what is this object? F13. Okay. So let us go back. F13. Epsilon 1, 3, then it has to be 2. But epsilon 1, 3, 2 is minus of epsilon 1, 2, 3. So it will be plus B2. Okay. So it will be BY. Okay, so it will be By. Okay. Then since it is antisymmetric matrix, it must be Bz. Then this will be 0. Okay. Then what will be F2, 3? F2, 3. F2, 3. F2, 3. So I2, 3, K is 1. But that is cyclic combination. So 1, 2, 3, 1 is same as 1, 2, 3. So I will get minus Bx. Okay. So it will be minus Bx. Okay. If this is By, then this will be minus By. Okay. If this is minus Bx, then this will be Bx, and it is 0. So I have a matrix for F mu. It's not a big deal. You just write the components in the matrix. That's it. What is important is that this object F mu nu, del mu a nu minus del nu a mu. Now you see, because of this, we know that how this transform under Lorentz transformation. Del x nu. How this will transform? This is in this notation. This will be del nu a mu. Now tell me how this quantity will transform. This quantity will transform as what? As a scalar, as a vector, what? How this quantity transform?
Tensor of rank 1.
This will transform as a tensor of rank 1, 1. Then how this quantity will transform?
2, 0.
Tensor of rank 2, 0. How this quantity will transform? Tensor of rank 2, 0. So this will be a tensor. So F mu nu is a tensor of rank 2, 0. If Ij is not a tensor, Lorentz tensor, okay? F mu nu is. Is that clear? If I0 is not a 3 vector under Lorentz transformation. Is that clear? Sorry, Fij is not a 4 vector under Lorentz transformation. This is, if you want, Fi0 will transform as a vector, under rotation, but not under Lorentz transformation. Under Lorentz transformation, this should transform as a 4 vector, but this is not transform as a, this will not transform as a 4 vector. Only when a vector transform as a 4 vector under Lorentz transformation, then you say that that quantity is a 4 vector. Okay, so this F mu nu is a tensor. That is the important thing. Okay. If F mu nu is the tensor, then what will be F lower mu nu? It will be a tensor of rank 0, 2, right? Okay. So F mu nu will be, you have to lower these indices. Okay, how to lower these indices? We know how to lower. F mu rho, F nu sigma, F rho sigma. So you can also write the matrix for F mu nu. You write that. I will leave it to you. It is very simple thing to do. Is this clear? Now, after doing this, you consider, you go back to our equations of motions. These. Okay, so now I will concentrate on equations of motion. Okay, consider dE by dt equal to E times V dot electric field E. Okay, let us. So this is nothing but E, VI, ER. EI you replace by FI0. So it will be E, VI, FI0. And VI is what? VI is dxi by dt. Okay. But this is nothing but 1 over gamma times dxi by d tau, which is nothing but 1 over gamma times ui. Spatial component of 4 velocity. Okay. So dE by dt. Okay. So again, I can also simplify this also. Okay. What is your dE by dt? dE by dt is dE by d tau, okay, and d tau by dt. Okay. So this is equal to, okay, so this is nothing but 1 over gamma dE by d tau. Okay, is that clear? Okay, but this is nothing but P0 is E by C. So E is C times P0. Okay, it will be C by gamma dP0 by d tau using this relation. Okay. But this is equal to VI. VI is 1 over gamma UI. Okay, so 1 over gamma UI and FI0. Okay. Now this is, see, there is a difference. There is no meaning to raise and lower the indices on V, because V does not transform as a 4 vector, spatial component of 4 vector. Okay, these are ordinary these velocities. Okay, but on the other hand, this UI transform as a spatial component of 4 vector. Those two things are different. It makes sense to raise and lower the index on U. It does not make sense to raise and lower index on V. Okay, so this implies that dP0 by d tau is what? dP0 by d tau will be equal to minus E by C. I will substitute everything here. Okay. So I have to put E here. E is there. Is E by C. Okay. Gamma will go. So E by C del xi by del tau Fi0. This is nothing but minus so why I'm putting minus sign? Why there is a minus sign? There should not be any minus sign. Yeah.
After lowering the index, there will be a minus.
Huh?
After lowering the index, there will be a minus.
After lowering the index, I will get minus sign, but I will lower it. Okay. So this will be UI, okay, and Fi0, but Fi0 is minus of Fi0. Then I have to put minus sign here. Okay. Then I have to put minus sign here. Okay. But Fi0 is nothing but F0i. Okay. So it will minus of F0i. So it will be plus E by C UI F0i. Okay. So this is the relation for zeroth component of 4 momentum. Okay, clear? But there is a problem because there is not a C. Yeah. So if I want to write this also in terms of zeroth component of 4 velocity, then there will be m difference. So P0 is m. So it will be, if I want to write U0 du0 by d tau, this I will get E by mc ui f0i. That's it. Either you use this or this, it doesn't matter. I just zeroth component of 4 momentum, just zeroth component of 4 velocity. Okay. Now you consider the next relation. dp by dt equal to E plus E by C V cross V. Use the similar step as we have done here. Okay. So this I will leave it as exercise. So difficult part I am leaving for you. Okay. So it's not that difficult. It is slightly complicated calculation wise. Okay. So show that one can write this as dui by dt. Okay. dui by d tau. Okay. dui by dt is covariant. So dui by d tau is equal to dui by d tau is equal to E by mc, okay, u alpha, f I alpha. Where alpha runs from 0, 1, 2, 3. Okay, so this you show. Okay, this is your exercise. Okay. So what you need to do, you have to substitute the expression for V cross B. V cross B is equal to, take ith component of this, the ith component of electric field. You know how to express electric field in terms of F. Okay, then concentrate on V cross B. Ith component of this is epsilon ijk bk. Okay, Vz bk. Okay, then bk you express, you know how to express bk in terms of F. Use that, you will get the product of these epsilons. Use the expression for product of epsilons. Okay, and you derive this result. And you ultimately you will get the result for this dui by d tau. Okay. So look at this equation and this relation. Okay. So if you combine this and this page is not working. If you combine this and the last one, you will get, you can write du mu by d tau is equal to E by mc u alpha u nu f mu nu. Okay, or in other words, you can also write in equivalent way d u mu by d tau is equal to E by mc. Okay, f you can write this as f mu nu u nu. Anything you can do. Okay, since these are tensors now, you have to keep track of indices only. Okay, if a certain equation is a tensor equation, then it should have same upper and same lower indices on both sides. Okay, so mu is a free index here, and it is occurring as a superscript. It should occur as a superscript on the right hand side. There are no other indices. So whatever the indices on the right hand side, they are either not there or they are summed over. So here the nu is summed over. So this is a correct tensor equation. Another advantage of this equation is that once you write this in one frame, this relation, it holds in every frame, because we know how one frame is related to any inner frame is related to the rest frame. We know how that relation is. That is Lorentz transformation, boosts. Okay, and we know these are Lorentz tensors and Lorentz vectors, or 4 vector and 4 tensors. Okay, we know how they transform under Lorentz transformation. So on the both side, the Lorentz transformation will get implemented. Okay, and the result, the central result will remain same. Okay, is this clear? Okay, so these are the covariant form of equation of motion for a relativistic particle moving in the external electromagnetic field. Okay. Now from here one can consider special cases. You consider constant electric field. Okay. B is 0 and electric field is constant. That is not changing with time, and uniform. That is not changing with space. So you have like capacitor kind of situation. Okay, and write down this equation. Solve them. But these electromagnetic fields are external, and I already explained what is the meaning of saying external. Word external here. Then you consider E is 0 and magnetic field is uniform. Constant uniform magnetic field. Okay. Then you consider the situation where electric field is static but not uniform. That is electric field of point charge, but B is 0. That you can consider and write down the equation of motion. Okay. Is it clear? So these are the covariant form of equation of motion. Equations of motion. Any doubt so far? So we are not going to do that. Okay, if you are interested, you can do in the exam. Some problem might occur. Okay, I may give some problem. So it's your responsibility to open the Jackson and see there. It's given there. So many things are discussed in the Jackson. You use Jackson or Landau Lipschitz. It's given there. Okay. Detailed detailed solutions of equation of motion. Okay. Any questions so far? Should I proceed? If you have any questions, then I will stop. Otherwise, I will proceed.
Sure, you will proceed, sir.
Proceed? Should I
proceed? Yeah. Yes, sir.
So give me a minute. Just So now what we are going to do, we'll discuss more about the field strength tensor. We'll discuss more about the field strength tensor. Okay. So let me do that. So so we have a tensor defined F mu, second rank tensor del mu a nu minus del nu a mu, which is called the field strength tensor. Okay. So basically, you are writing electric and magnetic field in a you are accounting for the electric and magnetic field through this field strength tensor. The advantage of working with this is that, as the name suggests, it transforms as a 4 tensor under Lagrange transformation, while electric field and magnetic fields are not. Okay, you must understand this. Like E and B will transform like, you remember this, your velocity, 3 velocity transform under Lagrange transformation in a slightly complicated way, right? The transformation rule, if you go back to our first 2 lectures, the transformation rule for this velocity is complicated. It's not like your 4 velocities, 3 component of 4 velocities. 3 component of 4 velocity will transform like lambda I alpha u alpha. Okay? This rule is different than the rule of usual velocity transformation. Similarly, your electric field and magnetic field will transform in a complicated way. They won't transform as a 3 component of some 4 vector. Okay. Now, by looking at this tensor, okay, we also can write that I already explained anyway. We can also write F mu as eta mu rho eta nu sigma F rho sigma. Okay. Now one can define. Okay, one can define. I will state that, and explanation of this I will give later on. Okay. Suppose if I define, okay, maybe I will postpone this discussion because I need to define epsilon symbol in 4 dimensions. Okay, that I will postpone. Okay. So the next thing after you define this field strength tensor, okay, is to write the Maxwell's equation. Okay. So far we are not discussing about the dynamics of electromagnetic field. In this sense, my electromagnetic field which is occurring here were assumed to be external. Okay. There is no dynamics at all in the electric and magnetic field. Okay, right? So now we will discuss the dynamics of electromagnetic field. Electromagnetic field. Okay, and obviously I will discuss in terms of this F mu. And in the process we will see some properties of F mu. Okay. What are your Maxwell's equations? You tell me the Maxwell. Okay. By the way, I need to now be careful about the units. Okay. So in SI units, your Maxwell's equations are del dot E equal to 1 over 4 pi epsilon 0 rho. Okay. Then del dot B equal to 0. Okay. Then del cross E, del cross B is equal to mu 0 over 4 pi J0, sorry, vector J plus mu 0 epsilon 0. This is the permeability of magnetic field and this is permittivity of free space. Sorry, this is what I forgot the name. This is permittivity of free space and this is permeability of magnetic. Correct. Okay. And del E by del T. Okay. And del cross E is equal to minus del B by del T. Okay, these are the Maxwell's equation in SI unit. Jackson uses Maxwell's equation or everything in terms of Gaussian units. Okay, in the Gaussian units you have, so whatever we are doing till so far it was in Gaussian units. Okay, in the Gaussian units you have del dot E equal to 4 pi rho. Okay, then del dot B, there is no difference. Del dot B is always 0. Then del cross B is equal to 4 pi by C, okay, J, okay, plus 1 over C del E by del T, and del cross E equal to minus 1 over C del B by del T. So these are your Maxwell's equations. Okay. And now I will use different unit system. Okay, I will use Heaviside Lagrange units. It is given in the appendix of conversion from SI to Gaussian, Gaussian to Heaviside Lagrange unit. It is given in the appendix of J.D. Jackson. Okay. In the Heaviside Lagrange units, okay, del dot E, these are rationalized units in the sense that these 4 pi factors won't come. Okay, the units are arranged in such a way that these 4 pi factors won't come. So del dot E equal to rho. Okay, del cross B equal to 1 over J by C plus 1 over C del E by del T. Okay, del dot B equal to 0. It is always 0. And del cross E is equal to minus 1 over C del B by del T. Okay, so these are the Heaviside Lagrange units where this 4 pi factor won't come. Okay, these we don't even use. Okay, these are for engineers. Okay, one can use. It is for application when you derive some experimental quantity. Okay, in the experiments you use this. Or even these are also useful. Okay. These are particularly useful to discuss theoretical subjects. Okay. In quantum field theory or in relativistic quantum mechanics, okay, we use this Heaviside Lagrange units. And afterwards, I will also put C equal to 1. Then we call Heaviside Lagrange units with C equal to 1 or Heaviside natural units. Okay, but that I will do afterwards because we want the feeling of C at the beginning. Okay. And then I will put C equal to 1 at the end. Okay, so we will work from now onwards. We will work here, and I will suggest you to this appendix of J.D. Jackson. Okay. Everything is given there. Okay. So now I want to write, see, you see, although these Maxwell's equations, it seems that they are not covariant. but they have not written in covariant language, but they are relativistically invariant equations. Not relativistically invariant, they are relativistically covariant equations. Covariant equations. They are relativistic covariant. It's not. It's the point is that they have not written in covariant form. These equations are true in any frame. Okay. If you get some results using these equations in one frame, that result holds in another frame. Okay. It's just that we have not written it in a proper tensorial form. It does not mean that they are incorrect or they are not Lorentz covariant. If certain conclusion is drawn from this Maxwell's equation in one frame, that conclusion or that rule will hold in any other Lorentz frame. In that sense, they are relativistically covariant. But they are not written in covariant form. So our first job is to write these equations in covariant form. Okay. Yeah. So for that, okay, let us start with first two equations. Okay. Let us start with these equations. Del dot, not first two, let us start with these equations. Del dot B equal to 0 and del cross E, homogeneous equations, homogeneous Maxwell's equation. Del cross E equal to minus 1 over C del B by del T. Our aim is to write these equations in vector potentials, four vector potential. You see, these expressions, you know dynamics. These are not dynamical equations actually. You see, these equation in fact gives you the redefinition of this equation, for example, give you the redefinition of magnetic field in terms of vector potential, right? Okay. Del dot B equal to 0 means B, you can write B as curl of A. So these are, there is no new information I'm obtaining from this equation. In the sense that these are not dynamical equations. Okay. For example, if you give me B at time t equal to 0, I cannot use this relation to obtain B at later time. Okay. So in a sense, these are not equation of motion for B. They will not tell you anything about the time evolution of B. They just tell you about the redefinition of B in terms of vector potential. Similarly, this relation also is not dynamical. Okay. One can write this, one can use this relation, okay, to express E as minus grad phi minus 1 over C del A by del T. That's it. So these two equations, homogeneous equations, are basically telling you the redefinitions of electric and magnetic field in terms of vector and scalar potential. Okay, these are not dynamical equations. Okay. This is what you can, this is what you get. Okay. In other words, these two, B and E, will solve this and this at all times. That means these B and E are the solutions of these two equations identically. Okay. You give me any electric field and you give me any magnetic field, I will say that these are the solutions of your E and B are the solutions of this. Okay. In that sense, these are not dynamical equations. Is this clear? It's not that we are obtaining the solution for electric and magnetic field, okay, by solving these two. Okay. I repeat, okay, because this is the important point. You consider any configuration of magnetic field and any configuration of electric field. Okay. When you substitute that here, it will always, these two equations are always satisfied. That means when I say any configuration of electric field, it means that it's not a solution. It's not a solution, right? Solution is a particular function, okay, which when substitute into differential equation, the differential equation is satisfied. Okay. So here any, you give me any B and any E, I substitute here and I will see that these two equations are satisfied. Any E and any B, when I say any E and any B, it is restricted to these. That B should be expressible as a curl of A and E should be expressible like this. Okay. Is this clear? So these just give you the redefinition of magnetic field and electric field in terms of phi and A. Clear? Okay. So you will not bother about this. We'll come to this equation later on. Consider this equation. Del dot E equal to rho. So when I say rho, it is a function of time and space. Okay. What is del dot E? Del dot E is del I EI is equal to rho. So this implies del I EI is what? EI is Fi0 is equal to rho. Okay. So del I is Fi0 is equal to rho. Okay. Now you consider the next relation. Okay. So this we have expressed in terms of F. Now you consider del cross B equal to J by C plus del E by del T. One more. Okay. Del cross B is epsilon I J K del J A K. Sorry, del J B K. Del J B K. This equal to, so I am concentrating on ith component of this equation. So this will be equal to Ji plus 1 over C del T is del 0. Okay, and EI is Fi0. Okay, so epsilon 0 I J K del J B K is 1 over C Ji plus del 0 Fi0. But what is BK? BK is in terms of F I have to write, so it will be epsilon I J K del J minus half, okay, and epsilon K L M F L M. Okay, there is a del J, so it will be F L M is equal to Ji by C plus del 0 Fi0. Okay, here. So you use now the property of product of two epsilons. Okay, so if you use that, okay, you will get, okay, minus half, okay, del J Fi0, okay, del J Fi0, okay, plus, so in fact you will get twice of, so let me do this carefully. Okay, so this is equal to minus half product of two epsilon, K is summed over, so it will be del I L del Jm minus del Im del Jl, okay, F del J here FLM equal to RHS. Now concentrate on concentrate only on LHS. Okay. So the LHS is equal to, so this implies minus half. Okay. So you see that L is replaced by I and M is replaced by J. So first term will give me del J F I J and second term will give me del J F Ji. Okay. So they will add. Okay, and I will get 2 factor. That 2 factor will cancel here. Okay, so I will get del J. So half will cancel. Okay, so I will get minus del J F I J, okay, minus del 0 F I 0. Okay, and there was this epsilon. Just a minute. Yeah, the epsilon has gone. So this is equal to Ji by C. Okay, so I have taken this side on the LHS. Okay, so now I will raise these 2 indices up. There should not be any sign change because there are 2 space indices. When I raise one, I will get minus. Another one, I will get minus. So resultant plus sign. So this is equal to minus del J F I J, okay, plus del 0 F I 0 equal to Ji by C. So this implies del mu F I mu equal to minus of Ji by C. Is this correct? This is nothing but, you see, the down index, this together with this. Okay, so if you expand these in components, you will get this relation. With minus sign extra, so I'll put minus sign extra here. Okay, so this relation together with this relation, I want to write in a combined way. So if you write it, you'll get, if you combine these 2 equations, you will get del mu. So instead of writing I in the first position, I will write I in the second position. So there will be plus sign. Okay, so F del mu F mu nu will be equal to J nu by C, where J nu is defined to be C times rho and vector J. So these are now these tensor equation represents 2 equations. Okay, these 2, this and this. These 2 equations are written in this. Okay, for nu equal to 0, you will get del dot E equal to 0, del dot E equal to rho, and for nu equal to any special index, you will get the ith component of curl of B. Okay, so this equation gives me the covariant form of inhomogeneous Maxwell equations. Inhomogeneous Maxwell equations means those equations having the source term. Okay. This rho is your charge source for charge, and J is the current source for current. Okay, so this and these are inhomogeneous equation. This one and this one. Okay. These are inhomogeneous equations. Good. So you have expressed the inhomogeneous Maxwell's equation in a covariant form. Okay. Any doubt so far? Or any question? Any question? Hello?
No, sir.
Okay. So now I will express the homogeneous equations and I will stop. I will write equivalent expression for homogeneous Maxwell's equation and I will stop. Okay. So now consider homogeneous equation, that is del dot B equal to 0 first. Okay. Del dot B equal to 0. Okay. B is what? B I is epsilon in terms of F. Bi is minus half epsilon I j k f j k. Okay. Yeah. So del dot B equal to 0. That means del I Bi equal to 0. It implies minus half epsilon I j k del I f j k is equal to 0. Okay. Clear? Okay. What conclusion you can draw from this? See, I can write this as, first of all, I can write this as epsilon I j k del I f j k is 0. Okay. This is totally antisymmetric tensor. This is totally antisymmetric symbol, or in a sense, this is totally antisymmetric matrix. So what do you expect about, what can you say about this?
Symmetric.
Huh? If I take the cyclic permutations of this, only this, you consider only this object. Okay, I, j, k, and if I cyclically permute them, and if I add them, I will get 0. See, this I can write as epsilon I j k divided by 3 into del I f j k, okay, plus if I take cyclic permutation, then it will be del j f k I plus del k f I j. This must be equal to 0. Agree? Because see, I can permute cyclically these indices. So how this term is obtained? First you write epsilon I j k del I f j k, okay, divided by 3, okay, plus you write second, what you do, you write, consider 1/3 epsilon k, okay, you consider the following, you consider epsilon j k I, okay, epsilon j k I, and all these three indices are summed over, epsilon j k I and del j k j del j f k I. Okay, you write this. There will be third term. Now you use the symmetry property of epsilon. Okay, epsilon j k I is the even permutation of epsilon I j k. Okay, so I will hop twice. Okay, so then I will take epsilon out, and this will remain as it is. Okay. Similarly for third term. So from each term, I have taken this epsilon out, and I have written in epsilon ijk. That's it. And this equal to 0 means then this equal to 0. Okay. See, epsilon, I hope you understand what I am saying. Okay. This implies that epsilon ijk, suppose if I put I equal to 1, okay, then j and k must be 2 and 3, and so on, 3 and 2 also. But in any case, this epsilon 1 to 3 is non-zero. For non-zero components of epsilon, I have this relation which is equal to 0. That means this quantity must be 0. This square bracketed quantity. Agree? Epsilon ijk will be 0. They will be anyway 0 if I and j are same. Okay? But when I, j, k are not same, okay, for that I will get what? Del I f j k plus del j f ki plus del k f ij equal to 0. Clear? If any of these two are equal, then anyway I will get 0 equal to 0 result. If any of these two indices are equal, then I will get 0 equal to 0 result. Because you see, f is also antisymmetric. Okay, so this is the equivalent way of saying this, but this is just an identity. Okay, this is just an identity. You use the antisymmetric property of f, and one can again show this. Okay? I have not used any dynamical information in this. Okay, it is just a statement that B can be expressed as a curl of A. It is equivalent statement. Okay, so I have not. This is identity. Okay, these plus this equal to 0 is identically hold for any configuration of B and any configuration of E. This will hold. Similarly, you consider now del cross E ith component. Okay, del cross E ith component to minus 1 over C del Pi by del T. This is minus del 0 Bi. And I want to convert in something like this. Let us see how to convert. Okay, so this is del cross E ith component. So it will be epsilon I j k del j ei. Ei is f I 0. Okay. Sorry, if ek will be f k 0. Okay. Clear? Plus, I will take this on the left hand side, plus del 0 bi. Bi is minus half epsilon I j k f j k. This is equal to 0. Okay, this implies twice of epsilon I j k, okay, del j f k 0. Okay, del j f k 0 is minus of del j f lower k 0. Okay, so this will be minus of del j f lower k 0. Okay, then I have, so twice I have written here, and I will write 0. So it will, this will be minus of epsilon I j k del 0 f j k, del 0 f j k, del 0 f j k. This is equal to 0. Okay, clear? Okay, so what I'm getting, So these two I will write in a slightly different way. This 2 times this I will write as minus epsilon I j k del j f k 0. Okay. Right. Okay, so just a minute, give me a second. Okay. So this will be so I will write this as minus epsilon I k j, okay, del k f j 0. Okay. Okay. This term I have written in terms of these two terms. Okay. Minus epsilon I j k del j f k 0 minus epsilon I j k I have written epsilon I. So I use just dummy indices. The fact that j and k are dummy. So this term is actually same as this one. Minus epsilon I j k del 0 f j k is equal to 0. But this term I will now use the antisymmetry property of epsilon I j k. Okay, and I will write this as I will write this term as, so I will write this equation as epsilon I j k del j f k 0. Okay, so minus plus minus, sorry, plus minus, sorry, we plus plus plus. Okay, then I will use antisymmetry of this, and it will be extra minus sign. Okay, so this will be minus epsilon I j k del k f j 0 minus epsilon I j k del 0 f j k. This is equal to 0. Is this clear? Okay. Now I will take epsilon common, epsilon I j k del j f k 0. Okay. Epsilon I j k del j f k 0 plus del k, sorry, will be yeah, del k f j 0 is plus of del k f 0 j. Okay, and plus, so I'm doing wrong here. There should be plus sign here. Plus, 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 and then I used antisymmetry in second term, so it's a minus here. So del j f k 0 plus del k f 0 j plus del 0 f j k. This is equal to 0. So we are near. Okay. Now if I define, let us define. Okay. Levi-Civita symbol actually turn out to be a tensor due to symbol in 4 dimensions. Okay. Epsilon mu nu rho sigma. Okay. It is defined like, okay, it will be equal to it is defined as equal to plus 1 for even permutations of 0, 1, 2, 3. It will be minus 1 for odd permutations of 0, 1, 2, 3. My battery is lower. Anyway, we'll finish it. And 0 for 0 otherwise. Okay. Now, epsilon 0 I j k will be what? This will be plus 1 for even permutations of 1, 2, 3. Okay. And minus 1 for odd permutations of 1, 2, 3 and 0 otherwise. Okay. Fine. So with the help of this symbol, 4-dimensional Levi-Civita symbol and Levi-Civita 4-dimension, what I'm going to do, I will consider this quantity epsilon mu nu rho sigma del nu f rho sigma. Okay. Fine. Okay. And I will take all the antisymmetric, all the cyclic permutations also. Del nu f rho sigma plus del rho f sigma nu, okay, plus del sigma f nu mu. nu rho. Okay. All the cyclic permutations of this del nu f rho sigma. This will be equal to what? What do you expect this is equal to? Let us see. If I substitute mu equal to 0, okay, then 0 should not occur for nu, rho, and sigma, right? Okay, so nu can be I, rho can be j, and sigma can be k. This is what can happen if mu equal to 0. So for that, mu equal to 0, I, j, k. What will be the result? It will be del j f del I f jk plus del j f ki plus del k f ij. This, okay. So for mu equal to 0, this will be equal to this. Okay, but this is 0 because of this relation. Okay, and I think my battery is down. Maybe it will go at any time. And mu equal to, if I put mu equal to I, okay, then 0 can occur at any of these indices. Okay, so nu can be 0, or rho can be 0, or sigma can be 0. Okay, so for mu equal to I, one can show. I will do it next time. Okay. For mu equal to I, one can show that this equation reduces to this relation. This relation, okay, this curl, okay, curly bracket. Okay, this implies that curly bracket is 0. So for mu equal to I will get this, which is 0, and for mu equal to 0, I will get, anyway I will get 0. Okay, this implies that these two equations, this as well as this one, that means this one, can be written in this form: epsilon mu nu rho sigma del nu f rho sigma plus del rho f sigma nu plus del sigma f nu rho, okay, equal to 0. Okay, so your two homogeneous equations actually mean this. Okay, so they will not give any new information, but this is just the identity. Anyway, so I will stop here because my battery is very low. Okay, so I will stop here. If you have any question, you can ask quickly. Yeah. Otherwise, I will end the meeting. And our next class will be on Tuesday, either Monday or Tuesday. Tomorrow, I will not going to take any class.